My name is Alexander Korotkov. I'm the head of development in Postgres Professional. Today I'm going to talk about Credereum, Postgres with blockchain support. I know that it sounds provocative and even obscene to some, but I'm going to explain you better what we understand, how I understand it technically. Right now we see big hype around blockchain, and there are a lot of both supporters and critics of blockchain and cryptocurrencies. As we know, cryptocurrencies are now falling down on the downward curve, and a lot of people argue whether it's a permanent or temporary phenomenon. However, we are practical professionals. We are looking at blockchain practically from the point of view of how practicable it is for DBs and specifically to Postgres. And that is how we came up with a concept of Credereum. And the matter is that we decided to take ideas of blockchain and apply them to a relational DBMS and specifically to Postgres. These ideas are as follows. Well, I hope everything's okay. Probably I just started too early and not everyone has taken the seat. Okay. So in client-server model, in a DB, the user that uses DB trusts completely to the owner of the DB, trusts the data that DB provides, checks the data, and in case the owner of the DB wants, the owner can trick the user in any way if there is such an intention. The data may be distorted, deleted, or, well, we can do whatever to the data. And the question is, can we actually change this model so that the user would not have to trust the owner of the DB completely? The solution of blockchain, in fact, is the digital signature. So we have a digital signature for every transaction that the user performs. And the DB does not only give the reply for a query, it also presents a proof presented by the digital signature. But the system remains centralized because we have the owner of the DB, and the owner is responsible for maintenance and availability of this DB. And at the same time, we keep the privacy of the data, and not all the users see all the data. But at the same time, the owner of the DB presents a proof that the response to the query is correct, and the user has an opportunity to check on the response. So simplistically, the scheme looks as follows. So the user sends to the base not just a query. He does not simply perform a transaction. He receives the acknowledgement of commit, and if another user sends a query, he gets the response query result with a proof, with a chain of signed transactions that produce this very result. But this is the solution for only part of the problem. If we take an abstract from the initial article on Bitcoin, the first part is basically telling us that for peer-to-peer payments we need digital signature. Okay, we understand that. We understand how we can use that concept for DBs. And the next part is that we need to solve the double spending problem, and that is why actually we use the concept of proof of work. How double spending problem and the solution can be applied to relational DB. What can be considered to be double spending with DB? Double spending for relational DB is the possibility for the owner of the DB to branch its state into several states and to show one version of data to one user and another version of the data to another user. Say a user performs a transaction. This transaction, the result of this transaction is available for someone, and the other user sees the version without this transaction. And this is actually an opportunity for the owner of the DB to trick users, even if they use digital signature. That is why we produced a solution where the DB is going to send its decision to a hash, so all the data will be hashed, and the hash of the top level will be put to the trusted storage, reliable storage, and we know that we trust the storage. We know that this hash will be present in the single version there, so there won't be one hash and then this hash will is changed for another one. So there won't be any historical sequence of hashes. For example, hash number 10 of this DB with this value, it will be there all the time, and we trust this storage in this way. For example, the storage may be a public blockchain. Say, in Ethereum, we can make a key storage and keep these hashes there, or this can be a cloud you trust. Anything.
And correspondingly, when the user checks the response from database, he also correspondingly is checking not only the proof that he got from database, but he compares proof with hashes from trusted storage. But to understand this, I think we need to go into details. We need to understand how the hash is built and how to understand that the hash that was stored yesterday is the hash that will be the same in the future. To go deeper, we need a small introduction on Merkle tree or Merklix. It is the merge between Merkle and Radix. Merkle tree is a tree of hash that is applied to some blobs, so huge binary files. Like the torrents use Merkle tree. You can imagine a huge file that is hierarchically cached, and these hashes are reassembled into a huge hash of high level. Merklix is the same, but applied to key value storages. That means we have a set of key value names. Upon of them, we built the radix tree, the tree of prefixes. And for this tree, we then calculate hashes. Hash for every node is calculated as the hash of daughter prefix plus hash from the correspondent node, and so on for other nodes. And in list we have definitions derived from hash. So that means that the hash of the upper level is derived from the key value storage. The hash of every subtree is calculated from the subtree from the key value parts under this tree. And the peculiarity of this tree is that we can build the so-called miracle proof. That means we don't need to show the whole tree, but we can prove that under the hash of an upper level we have a defined number of hashes. This is the miracle proof, and it is used in blockchain, for example, for a user having a small volume of operative memory to be able to prove the whole memory of the user who owns the whole tree. So the user receives proofs and can check the proofs, although he does not have enough memory for this. And we want to apply this miracle tree for other purposes. Not to work with memory, but to work with privacy. For you, it is a great opportunity for user not to show all the data when user signs transaction. This is how the miracle tree looks like in the view of the user when user signs transaction. The signature is something that transfers the database from one level to another. So we can imagine any model of data and create a key value on the basis of this database of this data. We can choose one data key as the key, and as value we can and value will be in lines. So the user signs his the transfer of a base from one hash level to the other. That means that the user has changed some lines, and he then receives miracle proof showing that the lines previously had previously were not the same, that the lines are refreshed. And after the owner receives 2 hash for his signature, he must check them and send his digital signature to the bases. What does he need to check? We understand that the user needs to check the structure, the correspondence of one hash to the other, and he needs to see that the data is altered and that the new data is already in the database. And there are also the so-called hanging nodes responsible for the parts of data that are not seen by the user. And for them, the user should only see that they are the same, that he took a part of the base and altered only this particular part of the base, and then he can sign the transaction. Actually, we could bind the transactions, or bind all the transactions of the user, but there is a concurrency problem, because we need to lock everything for the time when the check is going. So we just take this transaction, pack them into blocks, and the transactions blocks should be independent, should not depend on each other. And these transactions are not contradicting. We can merge them, and the owner of the base can build some proofs stating that after use of the transactions, like by showing miracle proofs, he can show that the database is now in another state. Now I want to speak with you about trusted storage. It packs the transactions in blocks, makes a list of the transactions, and periodically hash is stored into the trusted storage, the hash of every block of the next block. And further, user can use this block for a check to check the procedure. So promptly speaking, we can see it on the basis of an example, not on a new system, but on a warehousing management system. And here, if we see a compromised database, someone can trick us in this database, take an old operation, and then in the end, it will be not easy for us to distinguish what did happen actually. Shall every action in this database be made consequently with use of digital signature, we can easily understand what were the incorrect changes in database and whose key has been used for this. Say there is an audit, and we want to check what was the alteration of the state of database or of its part for a limited period of time. And during this period of time, hash levels were stored in the trusted storage. Like from this block, the hash from this block and from this block is stored. How the proofs are built up by the base. For each block, we receive miracle proofs showing that, please take a look in the frames of this block, the following transactions were performed, and the lines, the corresponding lines were changed. This will be the same for all blocks, with miracle proofs, with digital signatures of transactions, with hashes from blocks, and these hashes are proven to be the same hashes that are stored in a trusted storage. So on the basis of digital signatures and hash, we can let the users check it. So this was the idea, the theoretic part. And now I want to present you the prototype that is developed by us in Postgres. So as I already told, for us to use all the trees, we need to transfer base to the format key notion. The prototype looks like this: key relation and qualified scheme with ID of row as an 64-bit integer. This is the limitation of the realization, the current realization, but we can support any other primary keys. So this is how the tree looks like. We have a routing in tables, and when the tables are there, the subtree is responsible for lines of a defined table. This is how the database is distributed on one tree. The prototype is not really optimized for now, so we just store the tree as an SQL table with a key, with a massive of shortcuts for the children. Lines are of various formats, so we use the coding in JSON. This is an ordinary Postgres extension. It's not published. This is a private repository where you can not find it, but in 2 or 3 weeks after the conference, When we will be ready, we will publish it on GitHub, and everyone will get the possibility to download it. It is the standard installation, like make, install, install, check. You create the extension, and then you just, for the tables that you want to cryptographically audit, you just pose a trigger after the basic operations like insert, update. And this trigger inside of itself performs all the work with tree and with digital signatures. The use looks like this. You open a transaction, you make something with a table that is subject to cryptographic audit. If we would commit it, it would be a mistake. So we just ask for a special function with return of change set, represented by the two miracle proofs as I already showed you. Then our application should make it valid, sign it, and when the signature is obtained, we are passing to the function of signature with public key or with the current signature of a current transaction. Then the base must check the signature. If there are no mistakes, you can commit the transaction. So this is the Python view of how such application can be created. We just connect to the database, made insert, the transaction is now open, and we have a small library that takes this change set, represented as miracle proofs, and then we receive the result as a set of updates and inserts that were made in the database. And then we need a code that will check that nothing else is in change set and that the changes that were made is really there. Then the digital signature and execution of transaction signature upon the transaction with public key and signature. So I think you've already mentioned that the developer must make his work twice. So first you create something, then you need to introduce a code that will check it. It's not convenient, it's inconvenient, therefore you need to introduce something like ORM when you change data, and the application reminds you of of your work between you and client, but this needs to be developed. Limitations. There are, of course, limitations. The first limitation is that the sub-branches of miracle proof open coverage channel for data information that is not seen by the user. That means user doesn't see some subtree, but user sees hash and user can register whether hash is changed or not after the last transaction. The user can see a prefix. There is some coverage channel. It's not a full opening of data, but still leakage is possible. The third limitation is in digital signature. The digital signature must be executed on the side of the end user to work correctly. If we are speaking about application for smartphone, that means that the end user must generate his own key, and this demands for a higher operating culture, comparing with regular applications. And the main limitation is that it's uneasy to prove the story, because it's directly proportional to the whole history of transaction that is changed. That means that the database to generate all the proofs must go through all the proof and must generate a whole bunch of miracle proofs to close it. And this is a problem. But we don't need to forget that the operation of writing are not subject to this, that the user signs the proof that is generated in a matter of seconds. And the second thing is that this is an optional way. If the user doesn't want to check the data for a long period, the user can make validation for the last 2 or 3 years, and such kind of proof can be generated more rapidly. And there are some ways to solve the complexity of proofs, like, for example, the owner of database can generate and filter to change the lines that were changed. Of course, you can make a fraud out of this filter, but the user can ask for all blocks that are needed for Bloom filter, plus additionally some blocks. That means this will be the separate control, and if the owner of a base will make a fraud out of filters, we still will be able to find the owner, such owner. Or the user can store a replica of database or accept updates and not ask every time for the whole story and store it at his part.
Speaking about where it can develop to in the future, from the point of view of blockchain, then this trusted place where we will be sending hashes and DBs, this could be a public blockchain. In addition to that, if we have a lot of DBs and everyone will be saving their hashes there may be a problem of scaling, and sharding can be required, but this will be a private case of sharding. We will have to save really those parts of hashes, and here this particular task for sharding is much more solvable than those that Ethereum attempts to solve, because there everything is much more complicated. We also need a security cloud where the owner of the DB can put his backups so that they are secured by encrypted checksums. And after audit, after seeing that from some point on hash does not correspond, say someone got in and changed something, the owner of the DB can recover everything from the cloud and thus reach consistency. Summarizing, well, Credereum is a tool that gives the owner an opportunity to prove the correctness of the data, and to the user it gives the ability to check on the data, and we don't have to simply trust 100% to the owner of the DB. There is a problem of the singleness of the DB status, and this is solved by trusted storage, the third party, but it is not needed in some cases. Say, sometimes it is enough to have a digital signature. And they do not need any additional protection from the database being doubled or split. For example, if you prove with a digital signature every line and you only add lines, for example, once we received a request about medical contracts. As they only add data there, if the owner of the DB decides to branch its state and show one state to one user and the other state to the other user, both users will understand that something's wrong here because there are too few lines here. So for this case, this risk is considered to be not significant and we do not need trusted storage. Performance for building the proof. Well, as yet, it is not a problem. Well, it is a problem in general, but there are solutions to this problem that I've already mentioned. Speaking about the performance of this database in general, in fact, it will be, of course, lower related compared to a different DB because we need to calculate all the hashes, digital signatures. But if we compare it to what is happening in public blockchains and their transaction rate, it's several transactions per second. Here, it can be, of course, several times higher. Prototype, well, it will be shortly released at GitHub, and we are going to hold a separate meetup for that. Okay, that is it on my part. Thank you. I'm ready to take your questions. Well, you already mentioned medical contracts, but I mean, in general, it sounds like a cool technology, you know, but we do not understand use case because this is pure blockchain, the distributed public ledger, but here you have ledger with signatures, but it is centralized and controlled. So what kind of organizations are going to have this kind of ledgers? Where can we use it? Okay, I've already mentioned I cannot give you exact names, but say an organization that stores contracts of users, patients, for example, with their doctors. Say they have a need to have a blockchain and there we do not need trusted storage. Every record is signed and they are put in a chain so that the DB owner could not delete it. Okay, what if those are simple patients, simple people? What do they do to their signature after that? They take it to court, their signature. How does it work? Well, in fact, if you took it from that prospect, it should be taken as an evidence from the legal point of view. It's just that I cannot give you precise information on the part of the potential client that sent us this request. But for example, in Estonia, as far as I'm informed, every person receives an individual card, which is actually an ID, and it has digital signature. So this is already the reality. Every citizen has a digital signature, and it has legal power. As far as I understand, digital notary, that the format we've already mentioned, for example, every notary has his or her own catalog and proves the information that the client brings to the notary. Right, another good example. In fact, the purpose of my presentation was just to share ideas, to share our achievements and get feedback from you. So we would like to add your ideas to the list of potential cases. That is what I'm here for. Could you please tell us more about how you join transactions into a block? And you said that if there are no problems, everything's okay. What if there are problems? If there are problems, well, it's like repeatable its level of installation. It's just who decides what we cancel. For example, two competing sessions. So this is not transparent, right? Well, the client will get a refusal. It will be there will be an error on implementation. It's like repeatable read. The DB is going, if it takes the conflict and transactions, it's going to form a block that it will not be able to prove, and that is how it will be. It will be discredited. It has not been cancelled because the user has not signed it. At the moment, when the DB generates for the user hashes and Merkle proofs, it means that it can be accepted. If it conflicts with someone, then at the step of generating the proofs, the user will get notification about the error.
А игнорировать кого-то и никто
Ну, база данных,
не
да,
знает.
она, в принципе, может кого-то игнорировать. Ну, такая...
Well, and sometimes it can ignore you, and you can't prove it. No, you can't prove it that you've been ignored.
К сожалению, эта проблема есть.
Даже не только эта проблема.
It is not only about this problem.
Тебя могут проигнорировать уже после того, как ты подписал.
You can also be ignored after you sign the transaction. That's this problem, in fact, it exists in blockchain as well. Signed transactions that had not yet been included into blockchain would not know what happens to them. In fact, there was an interesting work in public blockchains. There is quite a good guarantee for the top level of all the signed transactions, but nothing prevents for peer-to-peer broadcast to cut one party from the public blockchain. And in fact, blockchain doesn't help there a lot. This is another field for research, and I do not know any solutions to that problem. If any of you know how to come over this problem, I would be very interested to listen to it. Well, this is an important comment. In fact, this is a limitation that exists in blockchain, and we simply inherited it. Thank you for your presentation. Case, I had a question. We touched upon medical topic. It was in hackathon, and we used blockchain there. Is it possible to build with Postgres a system where we have various operators, say several hospitals are joined into one network, and one hospital can add data to the general network, but they can only load the history of a specific patient? Right. In fact, that is what we developed this solution for, because its advantage is keeping privacy. At the side of the DB, we solved the problem of giving rights and limiting rights. Okay, yeah. For example, we planned it that only doctors could see the history of the client, and they can trace where the change was introduced. Okay, yeah, and after my presentation we can continue the discussion of this case. I have two questions. Am I getting you right that encrypting, hashing, all that is performed by the client and the DB? In your solution, do you have a possibility to select the encrypting algorithm? Well, in fact, this solution, it needs two mechanisms. It has to have digital encrypting algorithm and a digital signature. If you don't like RSA digital signature, you can use a different one. The second question is about making blocks. Say several clients, several users update one and the same line at the same moment. In your implementation, you use row ID. Probably you need to have primary key for every table, or you take tuple ID. Okay, the limitation is that for every block, one line can only be changed once. Okay, if you take blockchain, you send a transaction to the pool and then wait for the response. Okay, here you do not have limitation by blocks. Blocks are actually created for concurrency. They are not distributed, they are just formed at the level of DB, and the external storage receives not all the blocks. This is the matter of intra-base, intra-DB performance. Blocks can be made quite often, every second, every several seconds. The early prototype that is not yet fit to assess performance, because there we also implemented a tree with tables, and this is a big overhead, and finally we will have a separate storage for this tree with the maximum performance. However, here the block, it will not be the cause of long delay, like several seconds. Okay, thanks. More questions? Hash block. What does it consist of? In the picture, we see the hash of the block, but in fact, the hash has to have the hash of the previous block. Okay. Hash. It is taken from the hash of the previous block and all the transactions that are part to it. Okay, then I have a question to slide 14. It is difficult for us to fake a transaction in a block or the last 5 blocks. For example, I have those illegal intentions. I want to forge the DB. In fact, here we do not present the proof of work. It is not a problem, but it must be a problem. Well, you know, the matter is that transactions are signed by the user, and they are signed for this hash of the block, and you cannot use them if the previous block is cancelled. Trust of storage, it should not be, you know, it is not a stupid storage where you can fake anything. It must be a storage that receives hash with a specific number from this DB owner only once. Okay, I do not get this very part. Say I have wrong intentions. I'm the owner of the DB. Say I'm the state insurance, I don't know, and I store there my medical contracts, any contracts, whatever. And I want to change, which is strange, but still, I want to change something 7 or 8 blocks before. And it means that I need to recalculate all the previous hashes, and it should be very complicated, almost implausible. But say I've done that, I recalculated all the hashes, and say we have a very trusted storage that stores all these hashes, the good hashes. So I recalculated them, and I cannot change them, no matter how it is implemented in trusted storage. There may be another blockchain or whatever. But I changed my DB, and my DB is now consistent. Say I've done it, all the hashes. But the user then will check with trusted storage. Okay, the user checks with trusted storage. So there are 2 generals, right? Trusted base and trusted DB and trusted storage. And say the user for some reasons trusts the storage only. How can we understand what was changed in the base? The base is already consistent. I do not know how we can do that, how we can recalculate all the hashes, but still, in case this happens. Well, if someone recalculated all the hashes and, for example, he deleted everything, we cannot understand what is wrong with this DB then. As a solution to this problem, in fact, we were looking at another storage, another trusted storage with continuous backup of all this thing. So this is just yet another copy of this DB, right? This is not the storage of hashes. Right. Because the storage of hashes can only explain the user whether everything's okay or something's wrong. If something's wrong,
уже не может
the
понять,
user
что пошло не
cannot
так.
really get
Это в
what
данном
is
случае,
wrong.
если владелец базы, да, если он все-таки не злонамеренный, там,
If the
например,
DB owner, if it is not because of wrong intentions, but for example, the DB was just hacked, the owner can raise the backups and look at what happens to hashes. So in general, you do MD5 of the whole DB. Then I do not know what you need hashes for. Okay, thanks.
В общем, если я правильно понимаю, отделение на блоки было сделано для
If
того,
I get
чтобы
it
каждый раз не
correctly,
пересчитывать Merkle 3 всей
you
базы.
divide it to blocks, not to recalculate Merkle 3 of the whole DB all the time. No, it is not exactly so. You'll have to recalculate Merkle 3. We did it. Just give me a moment.
Идея в том, что вот мы
The idea was that at some point
послали пользователю вот
we send
там старый хэш, новый
to
хэш,
the
и он
user
определяет
the new hash and the old hash.
и подписывает.
He checks these hashes and signs
Если не
them.
делать блоков,
And
то
if
получается,
you
что мы должны
do
на
not
этот
do
момент
blocks,
времени всю
it
базу,
means that
заморозить.
at this point of time you need to freeze the whole DB and wait till it's signed, because you can only tie the next transaction to this one. Okay, right now we have this guy's hash graph. Instead of calculating the whole tree, they do something more interesting. It's similar to Git. There you can calculate, as far as I understand, proof structure for every snapshot. At the beginning of snapshot, you calculate the hash of all of it, and then instead of storing linear blocks, we store branches of the transition state, and then you don't need to break them into blocks. Okay, thanks.
Thank you. I will take a look at this. One more question? As a matter of fact, we monitor this topic, and now today we won't tell anything. We don't want to provoke you. Perhaps you have another database. Yes, we make monitoring, but I did not manage to see something like this, like Oracle. Yes, I think Oracle makes the same things, but these hybrid solutions, the attempt to mix blockchain with classical DBs, we can find them. Some project from Pavel Durov, but it's another type of mixture. Did you read these white papers? Yes, I read them, but I won't comment on this. We can speak separately about this. Tell me, is it possible to check only a part of the data? Actually, yes. Yes, but may we go down? May we check separate lines, the story of separate lines? Yes, database generates proofs for lines that were asked. Yes, this is the line proof. Some more questions, please? So, thank you very much.